day guys. So by today we look into the code. So we have started with the number system. We have seen the various number system that which is quite important in the computer architecture. Now we look into this code. We do have a different code. Why? Because various information has to be stored, processed by the machine, right? So in order to have different kinds of information to be get stored and processed by the computer hardware, the digital circuits, right, we do have a different code, right? In order to do that, the first one is a gray code. The second one, right, we don't have any order, but we are just seeing the different kinds of code, right? BCD, which is the shortest form for the binary coded decimal. Then we have XS3, and finally ASCII. Now we start with a gray code. It's simple, right? We do a XORing, that is XOR operation with adjacent bits. So for instance, right, we have 1101. Consider just given a bit, right? Now it is in the binary, and we know this is the bit position. Correct. It's 0, 1, 2, 3, and this is now in the binary, right? The base is 2. We need to convert to the gray code. Right. Now we have to start, right? You can say gray code we have to do, then which means gray code, right, for an understanding. So consider G3 is equal to B3. It's simple, right? So what is B3 over here? It's 1, or we can say it's an MSB. We can say it's a B3. So the MSB value, that is in this example, the bit 3 has to be taken as it is. Now, right, we have just taken like this. Now we need a gray code 2. So for that we have to do an XOR operation, that is B3 XOR B2. Then for gray code 1, we'll be doing an XOR operation between D2 XOR D1. Then for gray code 0, we are speaking about the present example, what we are looking into, right? D1 XOR D0. So this is the structure we need to follow in order to get the gray code substitution for the given number. So MSB has been retained. Now we are doing a XOR operation between the adjacent bits. So the MSB here is 1, and the next bit is the bit 2. So 1 cross 1, that is 1 XOR 1. If the inputs are same, then we'll be getting a 0. Now bit 2 XOR bit 1. So 1 XOR 0. If the inputs are if any one of the input is having 1, then the XOR output will be 1. Now bit 1 XOR bit 0, and again 0 XR 1 over here is 1. So this will be the equivalent, right? Right, this will be the equivalent gray code for the 1101. So we got the output 1, then 0, then 1, then 1. So this is the gray base. So to make it the clear final answer, the given is 1101, which is actually in the base 2. Now we have made it to the gray code representation. Right. So this is how the gray code representation will be carried on. Now BCD, binary coded decimal. For simple understanding, we can say a 4-bit representation of a digit, and the valid BCD is between 0 to 9. So this is quite important rule in the BCD. The valid representation, right, is between 0 to 9. The 4-bit representation from 0 to 4-bit representation of 9 is the valid BCD, binary coded decimal. Right. So now consider we are having a 2, 3, a decimal, right? A decimal. We know the base, right? Now we are going to convert to the BCD. So we take an individual digit in the given decimal, give the equivalent 4-bit, right? 4-bit for the decimal. So 0, 0, 1, 0, right? This is the equivalent 4-bit binary value for the decimal 2. And now at the hand we have a 3. So equivalent 4-bit is 0, 0, 1, 1. So now writing the final result, it's 0, 0, 1, 0, 0, 0, 1, 1. So this is how the binary coded decimal works. Now, to add a 1 point over here in this BCD, we have something called BCD correction. Means we already told that we have a valid BCD between 0 to 9. That is 4-bit representation of 0, 0, 0 to 4-bit representation of 9. Right? It should be like 1. Correct, na? 8421, right? So 1, 0, 0, 1, correct. So this will be the valid BCD number. Beyond that, if it is a 10, then that is not a valid BCD. So in that case, we have to add the obtained 4-bit to a 0110. That is actually a decimal is 6, right? To make it very clear, right? Say for instance, we are having a 2 decimal number, we are having a 3 decimal number. If we need to perform the BCD addition, what we used to do, we just have a 4-bit representation of a 2, which is 0010. We are having a 4-bit representation of 3, that is 0011. We are just performing a binary addition. For this, we obtain 1, 0, and 1 will be pushed as a carry, so 1 will be over here, and 0. So 0101, which is actually equivalent to the decimal 5. So this became a valid BCD. But if in case we do have another example like 5 plus 6, so now we do have a 4-bit representation for the 5 is 0101. So this is actually the decimal 5. We are making it as a BCD, that is a 4-bit representation. Now we are making a 6 to be a 4-bit representation. So we have like 0, 1, 1, 0, correct? So now if we go for the BCD addition, what happened? We have 1, 1, so 0, and this there will be a 1 carry, so we'll be having a 1. Now this 1, 0, 1, 1, it's not a valid BCD. Why? Because the BCD can have a only 4-bit representation, and the 4-bit representation should be between 0 to 9. That alone a valid BCD. But here 1011, it's not a valid BCD. Why? Because it is greater than 9, and this is a quite important rule in the BCD. So by this point of time, what we have to do? So we have to apply the BCD correction, that is 1011. So BCD correction can be applied by means of adding the resultant bits to a 0, 1, 1, 0. So now what happened? 1, 0, 1, 0. Now 1, 0 and 1 will be put onto the carry. Now this 1, it simply append 001 to make it as a 4-bit representation of the BCD, and which is subsequently called as a decimal 1, and 0, 0, 0, 1. And again this is valid BCD, and that represents the decimal value 1. So altogether we obtain the output as 11. Now which is the actual value of the 6 plus 5. So this is how the BCD correction will be applied for the non-valid BCD. It's quite simple. Remember of adding 6 or 01101, right, while we do a BCD correction, and this happens only when we go for the BCD addition. It's quite important whenever we get the result of the arithmetic additions. We have to remember whether the 4-bit is representing 0 to 9. If it is greater than 9, then we have to do a BCD correction. It's quite important point over there. Now we move on to a XS3 code. So it's very super cool code that comes under this code in computer architecture. So just consider like we have a decimal 3, right, and it's in the base of a 10. Now we need this to be converted to a XS3 code, right? So what we used to do, we just add 3 to the given number, that is 6. Now this 6 became a result of the XS3 code. It's simple, it's very obvious. Now say for an example, if we go with some binary kind, right, another example, we are having 1, 1, 0. What we used to do to make this as a, now consider this is in the base 2, now we need this to be in the XS3 code. We simply do a binary addition just by adding it up with a 3-bit 3 decimal binary representation. So 0, 1, 1, so which actually have, right, so 1, 0, 1, 0, 1. So this binary equivalent will be the XS3 code representation for 1102, right? Guys, remember we are not doing any addition, right? Remember we are not performing a binary addition in order to get the result. We are just making it easy to understand the given number adding with a 3. So any individual number has to be added with a 3 in order to get the XS3 code representation of the given number. It could be of a decimal, then go with a decimal addition of 3. If it is a binary, then go with the binary addition 3-bit or 4-bit, depends upon the input what we are getting it. So just that make the XS3 code. Now finally we move on to a ASCII. So it have its acronym that American Standard Code Information Interchange, right? It's a globally recognized value which we use to understand whenever we hit some character in the keyboard. It could be of a to Z, or small a to small z, or it could be a 0 to 9, or any special characters like a hash, dollar symbol, at the rate, and so on. Anything is treated as a character, and each character is having its own ASCII value. So again, for instance, right, just take it out, a capital A. We have the ASCII value for this A, that is 65. The binary, right, that is 65, and the binary equivalent, right, it would be something, right, I'm not sure about it. We are having some ones and zeros is the binary representation for the 65. So this ASCII code is the globally assigned value for each character. So any computer in the world, if you press A, then the ASCII code 65 will be processed by the computer hardware in order to store this A or to get the outcome as an A. So this is how the ASCII works off. So similarly, we have a small a have a different ASCII like 98 something, and similarly each character will be having a different ASCII value, and equivalent binary value will be get processed inside the computer hardware. So this how the different informations are processed in the computer hardware by means of the code what you have seen so far. So now we slowly move on to a Demorgans law, which is quite important when you build the circuits, right, especially with an NAND and a NOR. So while we had a discussion, we were very particularly highlighting this NAND and NOR or the universal gates. Why? Because the simplified circuit can be built only with a NAND and NOR. We doesn't depend on the AND or not. We can build with a NAND and NOR. So for that, remember this Demorgans law: A plus B whole dash is equal to A dash dot B dash. So guys, remember, here we have an addition operator, here we have a multiplication, that is dot operator. So even with the addition, the resultant would be the product multiplication. So this is how the Demorgans law works. And other hand, we have another law: A dot B the whole dash is equal to A dash plus B dash. So again, remember, here we do have a product, here we have a addition. So this two will make you to build any kind of Boolean expressions to be circuited only with a NAND or not. For instance, just imagine we need a dash to be implemented using a NAND gate. Is it possible? Why? Because the output of the NAND would be the product, right? And now we need a complement, that is inverse of a. So we have to use only the NAND logical gate to result the a complement, that is a dash. So whether it's possible is, of course it's possible. So by having a same input, that is a, to be inputted to the NAND gate, we get an output that is a inverse. So if you give the input as a 0, we get the output as 1. If we give the input as 1, then we get the output as 0. So this is how the NAND gate and NOR gate will be the universal gates, and it's quite easy to understand and simplify any kind of Boolean expression that can be easily circuited. The same way around for the OR gate too. The same input A can be given to a NOR gate and we get the output in the inverse pattern. So this is how the NAND and NOR gate will be works on. So apart, you guys might be remembering this AND gate, right? And then OR gate, and then one flip, that is NOT gate. So AND, it's a dot operator, or it's a addition, plus a NOT, it's just an inverse or flipping the bit. So these are the common logical gates but the universal gates or NAND and NOR, and you guys might remember the truth table, how to build for each logical gates. So apart, we have come across this XR, then we have come across this XNOR, and this XOR is what we have seen in the gray code. You guys might be remembering the truth table. We have A, B as an input, and XOR. So when we are having a same input, then the output would be 0, right? So when we are having any one input as 1, then the output will be 1. So again, became a 0. So the complete inverse, right, of this XR would be the X naught. So it's quite easy for you to understand. So for an understanding, right, so it would become 0, right? So what we have here, we have a 1 and then 0 0 1, the same for X naught. So this is how it's easy to understand the logical gates and the codes, what we have seen in the number system followed by the gates.